Swayam Prabha. Digital India. Educated India.
Today we will discuss something new, although related to induction, or more correctly the equivalent principle of Weyl ordering of Z plus or N or N0. So these are some fundamental properties integers. Okay, so there are quite a few results we will see. One by one, I introduce all the things. First, I introduce very important concept of divisibility. So, let us take two integers, a and b, positive, negative or 0. So we say that a divides b and denote this as if there exists an integer, let's say k, this can be positive, negative, 0, whatever, such that b can be written as a times k. So a divides b essentially means b is a multiple of a, or a is a divisor of b. But this is a little bit more general. So here are some examples. Let's say 5 divides 15. 5 divides minus 15, minus 5 divides 15, minus 5 divides minus 15, because every time you can find some k. Here the k is 3, here k is minus 3, this is minus 3, this is again plus 3. Okay, so this is a fairly straightforward concept. And I mention a set of properties of this divisibility. All these properties are very easy to prove, so I leave the proofs to you. All this will follow in a straightforward manner from the definition. First, for any integer a, 1 divides a. Second, any integer a divides 0. Then, if we have 3 integers a, b and c, and if it is that a divides b and b divides c, then a divides c. In other words, this divisibility is a transitive relation. Okay, what else I am missing? Okay, if a divides b, this implies A, the absolute value of A, is less than equal to absolute value of B. Okay, here I must make an assumption, B not equal to 0. Okay, so if A divides B and B not equal to 0, B is not equal to 0, then absolute value of A is less than equal to absolute value of B. 5, which property shall I, okay, A divides B and B divides A implies B is plus minus A. 6, this is already covered. A divides B implies A divides B times X for any integer X in Z. In fact, I can generalize this sixth result in this fashion. Suppose that A divides Bi for I equal to 1, 2 up to K. Then for any integers x1, x2 up to xk, we have A dividing b1 x1, b2 x2 plus so on bk xk. Okay, so I'll leave the proofs of these assertions to you as simple exercises. It simply follows from this definition. All the proofs follow simply from the definition. Okay, so now that we have a notion of divisibility, let us take a number n in Z plus, and let's say n greater than 1. N is called prime. If A divides n implies A is either 1 or A is n. And if n greater than 1 is not prime, it is called composite. So that means a composite number A, n, can be written as n equal to n1, n2 with 1 less than n1 less than n and 1 less than n2 less than n. Right. Okay. These are all elementary concepts. But given this, I prove the first very important theorem. If n greater than 1 is composite then n is divisible by a prime, call it P. Okay, so how do I prove this? It sounds obvious, but a formal proof requires some intricacies. Okay, so now I will use well ordering principle. Okay, so without this well ordering principle, essentially nothing useful will follow. So suppose S contained in Z plus, let be the set of integers greater than 1, let's say, that do not have prime divisors. Now, if this set S is non-empty, then by this well ordering principle, S contains a minimum element let us call this N. Okay. Now, okay, N cannot be prime because N itself, that prime itself divides that prime. So, N is not prime. Because if so, it has a prime divisor, namely itself. So, that means N is composite. That is, I can write N equal to N1, N2, where 1 less than N1 less than N, and likewise 1 less than N2 less than N. But note that this S contains all, I would say, integers that do not have prime divisors, and N is the minimum of them. Now, since N1 is less than N and N2 is less than N, each of these are not in S. So, in particular, irrespective of whether they are prime or not, N1 and N2 have prime divisors. Okay. So, N1 in particular does not belong to S because it is smaller than N. So, there exists some prime which divides N1. Moreover, you see that N1 divides N. So, together by transitivity, we show that P divides N, a contradiction. So, S must be empty. Okay, good. Okay. This is another important and interesting property of primes. This was proved by Euclid. There are infinitely many primes. So, how do I prove it? different color. Okay, maybe I restore to white. Okay, maybe I just give you Euclid's proof itself. I can proceed using a result I proved in a previous or earlier lecture, but anyway, let us follow Euclid's proof. Suppose that there are finitely many primes, P1, P2, up to Pk. Okay. Now I consider a number m, P1, P2, Pk, the product of all this finite number of primes, and I just add 1 to it. Now you see that P1 does not divide this quantity, it gives a remainder of 1, P2 does not divide, P3 does not divide, and so on. Pk does not divide this quantity. But by the previous theorem, there is a prime P such that P divides n, but this P is not equal to P1 or P2 or P3, so on up to Pk. So that is a contradiction. That is, we assume that there are only k primes, P1 through Pk, but this gives me another prime P which is not in this set. So this is basically a contradiction. This is Euclid's proof. Good. Okay. So, given this notion of divisibility, I introduce the notion of greatest common divisors or Gcds. Okay. Suppose that I am given two integers a and b, not both 0. One of them is allowed to be 0. Let us say they are in n0, but one may be 0, the other one is non-zero. Negative numbers we can handle, but anyway, for the moment let us not worry about negative numbers. Then we know that 1 divides any number, 1 divides a, 1 divides b, so which implies 1 is a common divisor. A and B. Maybe this comma is not needed here. Okay. So, now I keep on checking whether there is a bigger number which is a common divisor. Definitely I cannot go beyond the smaller of A and B if both are non-zero, otherwise that non-zero thing. Okay. So, if so, D is called the greatest common divisor or GCD of A and B if 1, D is a common divisor of A and B, and 2, if C is a common divisor of A and B, then there are two ways of saying it. C divides D, or I can say C less than equal to D. Okay. So this is an obvious concept. Okay. So we will see a couple of notes on Euclidean division on Gcds. So question is how to compute Gcd of AB in a reasonably efficient manner. Okay, incidentally, I also mentioned that Gcd of A and 0 for any positive integer A is taken as A for obvious reasons, whereas Gcd of 0, 0 is undefined. Because every integer divides 0, and therefore this, if I want to maximize over them, there is no upper bound. 1 divides 0, 2 divides 0, 3 divides 0, 4 divides 0. So any positive integer is a common divisor of this 0 and this 0. Therefore, the greatest of them makes no sense. So this is kept undefined. Okay, so now let us come back to our question, how to compute Gcd. For that we require something called Euclidean division. Okay. So, given any, this is again a theorem, A in Z and B in Z plus, there exist unique integers Q and R such that the following two conditions hold. 1. A can be written as Q times B plus R, and 2. 0 less than equal to R less than B. So you know this Q is called the quotient of Euclidean division of A by B. R is called the remainder of the Euclidean division of A by B. So Q is the quotient. And R is the remainder. Okay. So let me prove. So once again I will use the principle of OL ordering of Z class. Okay. Okay. I am on separate page, but still. Proof. First I will prove the existence of Q and R, and then I will prove their uniqueness. Okay. Okay. So, okay. So if B divides A, that is A is KB for some integer K, then I can take Q equal to K, R equal to 0. Okay. R may be 0, right, as we have seen. R may be 0, but less than B. Okay. So suppose B does not divide A. Now consider the set S of all A minus TB such that T is in Z and A minus TB, A minus TB is greater than 0. Then what happens? I have to show that S is non-empty. For example, if A is greater than 0, then if I take T equal to 0, then this is A, which is greater than 0. If A is equal to 0, take T equal to minus 1. Of course, in this case we can ignore because we have assumed that B does not divide A. Okay, but anyway, we can also handle this. So this does not arise actually under the assumption B does not divide A. On the other hand, if A is less than 0, take T sufficiently negative, something like maybe A minus A. Why this works? So A minus A is A plus AB, A times B plus 1. No. Sorry. A is negative already, so I should take T equal to A. T equal to A, sorry. Not minus A. A is already negative. So I take T equal to A. Then what is this? A minus TB is A minus AB. 1 minus B, A. Okay. So, B is greater than equal to 1, B is greater than 0. So, this quantity is non-negative, non-positive. This is negative. So, this is greater than equal to 0. And if I take slightly larger thing, A plus 1, this will become positive. Okay. Just one more, plus 1. It will be positive. Anyway, so okay. So this S is non-empty. Okay. Set of all A minus TB type of integers which are greater than 0. Therefore, again by the Euler ordering principle, S contains a minimum so let us call it R. Okay. So if R is greater than or equal to B, so we have a situation like this, R equal to A minus TB. And this is for some T, this is greater than or equal to B. But then if I consider this, A minus TB minus B is greater than or equal to 0. A minus T plus 1 B greater than or equal to 0. But since we are considering the fact that B is not a divisor of A, B does not divide A. This is actually the case that A minus T plus 1B If it is equal to 0, A is equal to t plus 1 times B. So it's greater than 0. And therefore, this quantity is again, this is in S, and it is nothing but R minus B, so smaller than R. Okay. So these two together, so this is a contradiction, therefore I must have R less than B. Okay. Now I prove the uniqueness. Now suppose that A can be written in two different ways. Two ways, let's say Q1B plus R1, Q2B plus R2, where R1 and R2 are in this range. But then if I subtract this quantity, I get Q1 minus Q2 times B, R2 minus R1. So in particular this says that B divides R2 minus R1. Okay. But R1 itself is less than B, R2 is itself less than B and non-negative quantity. So you can easily see that minus B less than R2 minus R1 less than B. This leaves us with only one choice, that is B divides 0. That is R2 minus R1 equal to 0. So R1 equal to R2. Now if I plug in this quantity here, R1 equal to R2, this will in turn give Q1 equal to Q2. Okay. So that's the proof of the Euclid's division theorem. Okay. Okay, so this essentially gives us the notion of Euclidean Gcd algorithm, which says that if I want to compute the Gcd of A and B, where B is greater than 0, then I can do it this way. A remainder B, or if you choose, you may call it A% B. Okay. So this is basically the idea behind Euclid's Gcd algorithm. Why does this algorithm terminate? Because you look at the second component B, and this is the remainder when something is divided by B. So this is less than B minus less than B, that is less than equal to B minus 1. Next time again you will get another remainder which is smaller than this, and this cannot proceed indefinitely. Eventually this algorithm will terminate. So it apparently says that you can have at most B iterations, but in reality the number of iterations is much less. But anyway, this terminates. Because the second component keeps on reducing. Okay. So maybe we investigate what is the best running time of this Euclidean Gcd algorithm. Let us not worry too much about this. I just mention an interesting result. let D be the GCD of A and B, then D is the smallest positive integer that can be expressed as this linear combination UA plus VB with U and V belonging to Z, set of integers. Why? Okay, so this is, we have spent quite some time on this U and V part, and we have proved constructively, that is using a couple of explicit algorithms, that this U and V exists. Okay, so definitely D can be expressed as UA plus VB. Then only thing that we want to establish now, that this is the smallest integer, smallest positive integer, which has this property. But that is quite obvious, because D is the GCD of A and B, and therefore D divides A, D divides B, and therefore any sum of this form UA plus VB with UV coming from Z is divisible by D. And therefore it follows that D is the smallest one. Okay. Okay. Again, given the concept of GCD, there is a very related concept, least common multiple, LCM. Okay, so it is LCM of A and B is the minimum of all integers M in Z plus, such that A divides M and B divides M. So M is a multiple of A and B, the smallest of this. Now, why is this set non-empty? Because, for example, it contains the product A and B, AB, which is the common multiple of A and B. Therefore, once again, by the Weyl ordering principle, this has a minimum element, that is the LCM of A and B. Okay, so I leave it to you as an exercise. To prove that AB is equal to GCD A comma B times LCM A comma B. Then this immediately gives us an algorithm for computing LCM. Given that, we can multiply integers and compute their GCD. Okay. So this is an algorithm for computing LCM. Okay, how much time do I have? Let me see. Okay, maybe a little bit time I have. So I can prove it. So this is the final and most important theorem. But before doing that, let me just recollect. So I have proved P prime and P divides a product AB implies P divides A or P divides B. Okay. In fact, I can generalize this result to this theorem. If P is a prime and P divides a product A1, A2, AK, then P divides AI for some I ranging from 1 through k. I am not going to prove it. It's a straightforward generalization of this. Maybe you work it out. Okay. Now, given all these things, I now have the tools to prove this important theorem, the fundamental theorem of arithmetic. It says that every n in Z plus can be factored uniquely into a product of primes. Okay, we know this, but possibly you have never seen a formal proof of this, so I will do it. Maybe I go to this one. So, proof. First, I will show that first show that there is existence, then I will talk about uniqueness. So, let us take some positive integer n. If it is prime, we are done. Itself is a, if it is 1, then this is an empty product. Okay, so let me write n equal to 1, empty product. N is prime. Then also we are done. So, suppose that n is composite. Okay. Actually, I am proceeding by induction, strong induction. So, this is the basis case. This you may also call as basis cases. If composite, n can be written as n1, n2. Sorry, let me. Okay, fine, no problem. n1, n2, or maybe I will do this way. We have proved some other thing. Any composite integer is divisible by a prime. I have proved it little earlier. So, n is divisible by some p. Prime p. Okay. But then, let us look at this n by p. This is smaller than n, and therefore, by induction, I can write it as product of primes p1, p2, pr. Then, n is nothing but a product of primes p, p1, p2, pr. Okay, so here I did never make an assumption that these primes are distinct from one another. Okay. In any case, this inductive proof says that any positive integers can be written as a product of primes. In fact, if I collect the equal primes in this factorization, I can write, okay, n as in this form. let's say P1 power exponent 1, P2 power E2, S power ES. Okay. Where I assume that P1 less than P2 less than PS. Okay. In order to prove this uniqueness, let us say that Pn has another factorization of the form Q1 power F1, Q2 power F2, Qt power Ft. Now once again I assume that Q1 less than Q2 up to Qt. Okay. Okay. Now let us consider P1. Okay. P1 divides this product, which in turn is equal to this. Okay. So P1 divides N. Okay. Which is equal to the second expression, which is a product of F1 plus F2 plus blah 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 up to Ft primes. Therefore, using this result, I think it is here, yeah, using this result, P is prime, then if P is prime and it divides a product, it divides at least one of these factors. So, using this result, P1 must divide some Qj. Okay. But this P1, Qj, these are both prime, so we must have P1 equal to Qj. Okay. Now, once again, if I do the same thing, Qj divides N. Okay. Qj divides N. Then, Qj divides this product, and once again, by this result, Qj must divide some Pi, that is Qj is equal to Pi. Okay. Now, if j is greater than 1, then I have P1 equal to Qj. By this is greater than Q1. Okay, I will use it, maybe I do this, greater than Qj divides N, so some Pi, Qj equal to Pi, maybe I press it this way, not this way. Okay, I want to use this result. Then Q1 is less than Qj, which is in turn Pi, which is Qj equal to Pi. I am making a small mistake somewhere. Qj equal to Pi, Pi is greater than equal to. Okay, so am I making any mistake? Of course I am making a mistake. Qj equal to Pi. Okay, Pi, I should have sufficient things. Pi equal to Pi. Okay. Actually, what I want to show is that this j is equal to 1. Without that, there is a problem. It's just playing with inequalities. I am quite P1, is equal to Qj, which is greater than Q1. Okay, maybe let us see. Let me list. Write the last. If I want to proceed like this, how is it? Then I will change this. I want to show P1 equal to Qj, which is greater than Q1, which is equal to Pi greater than equal to P1. Okay. So I do it for not Qj, I will do it for Q1. Not J, not J, not J. I will do it for Q1. So P1 divides n, so it must be equal to some Qj. Likewise, Q1 divides n, so it must be equal to some Pi. If j is greater than 1, then P1 is equal to Qj, which is greater than Q1, and Q1 is equal to Pi, which is greater than equal to P1. So P1 is greater than P1, which is a contradiction. Therefore, I must have j equal to 1. Okay. So this is almost done. So, so I have P1 equal to Q1. So if I look at this, n by P1 equal to, what did I add? P1 power E1 minus 1, P2 power E2, S power ES, and this is also same as n over Q1. This is Q1 power F1 minus 1, Q2 power F2, and so on up to Qt power Ft. Now if I use induction, strong induction, this quantity is smaller than n. Okay. So n by P1 or n by Q1, which is the same thing, this must have unique factorization. So in particular, it will prove that P1 is equal to Q1. Of course, you have already proved it. P2 is equal to Q2. Ps equal to Qt. S equal to T. E1 minus 1 is equal to F1 minus 1. E2 equal to F2, and so on. Es equal to Ft. Okay, so that's it. Again, by induction, which is equivalent to the well-ordering principle, I could now settle that every integer positive has a factorization, moreover, that is unique up to rearrangement of the prime divisors. Okay. So that is fine. I have just one more result I would like to cover. So maybe let me complete this, even if it exceeds 1 hour. Let me just complete it. Okay. So now, you are given a positive integer n, z plus. So all remainders possible are 0, 1, 2, up to n minus 1. So this is the all possible remainders. Let us denote this as Zn. Okay. Now out of these remainders, I ask the question, how many are coprime to n? That is Gcd of an equal to 1. So this set I denote by Zn star. This is the set of all a in Zn, all remainders, such that Gcd of an is equal to 1. It turns out that these two sets are very, very important, in particular in cryptography, computational number theory, in many other places. For example, RSA involves this, Diffie-Hellman involves this. There are lots of applications in cryptography. In particular, I ask the question, how many remainders are co-prime to n? In other words, I just define this as the size of this Zn star. Okay. This is called the Euler-tangent function, or the Euler phi function. Okay. So now that we have prime factorization with us, we can now derive an explicit formula for phi of n. But before doing that, let me give you an example. Let us say n is 20. Then Z20 is nothing but 0, 1, 2 up to 19. And Z20 star is all even numbers I should ignore. So out of 1, 3, 5 will not be there. 7, 9, 11, 13, 15 will not be there. 17 and 19. So it follows thus phi of 20 is 1, 2, 3, 4, 5, 6, 7, 8. 8. Okay. So in general, how we can work out a formula for phi of n? Let us see. Okay. So suppose n is p1 power e1, p2 power e2, ps power es. Okay. So p1, p2, p3 up to ps, these are all the distinct prime factors of n1. e1 can be anything, e2 can be anything positive. Okay. So now, if I want to compute phi of n, which is the size of the set Zn star, I proceed using the principle of inclusion and exclusion. First, I consider all elements of Zn. Then I have to subtract those that are in Zn, but not in Zn star. Okay. So which are they? They are not co-prime to n, which means they are either divisible by p1 or divisible by p2 or divisible by p3 and so on up to ps. So I will subtract all multiples of p1, all multiples of p2, and how many multiples of p1 are there? It is precisely n over p1. Okay. So it is summation n over pi over all I, running between 1 and s. But then those numbers that are multiples of 2 primes, like p1, p2, okay, they are subtracted twice, once for n by p1, once for n by p2, another time for n by p2. So I have to add them. pi, pj, I less than j, and this will continue, right? Minus summation is basically a triple sum over all I, j, k, n over pi, pj, pk, and this will continue. Okay. Okay. Now, you can easily see that this can be written as, this is the expansion of this. S. Okay. So this is the explicit formula. Given the time factorization of n, you can compute phi of n using this explicit formula. Sometimes this is written as n product of 1 minus 1 over p, and this product is over all prime divisors of n. So let us look at our example 20. 2 square times 5. So phi of 20 is 20 times 1 minus 1 over 2 times 1 over 1 minus 1 over 5. So this is half. 10 times 4 by 5 is 8, as it should be. Good. Okay, so that's I would say all about the properties of integers I wanted to talk about. In the next lecture, I will introduce something called a pigeonhole principle. Using the pigeonhole principle, we will prove some properties of just another important property of this Zn, which is called the Chinese remainder theorem. But this pigeonhole principle has many other applications, so we will see many other examples. Okay, so until then, goodbye.